Welcome back, everyone. Now, in this lesson, we're going to talk specifically about logarithmic graphs. So hopefully previously you already watched the exponential functions video, or you either have very extensive knowledge of exponential functions. So we're going to kind of just go right into it. So with logarithmic functions, we're going to look at the general form, which is going to be f of x equals a times log base b of x, where your b value is going to be your argument. Nope, your b value is your base, and your a value cannot be equal to 1. So your x value, in this case, this is what we're going to refer to as the argument. So with exponential functions are going to follow an add-multiply pattern. So meaning, specifically, if I look at this table here, we're going to go from 1 to 3 to 5 to 7 to 9. So this change would be plus 2, plus 2, plus 2, plus 2, so on and so on and so on and so on. And then if I look at the change in the y's, we're going from 2 to 4 to 8 to 16 to 32. So this change would be times 2, times 2, times 2, times 2. So if I do an example graph based on this table here, so that would give me the graph of y equals 2 raised to the x, which is going to look something like this. So we would have horizontal asymptote at 0. So y equals 0. And then our points, so the y-intercept would be at 0, 0, 1. And then if I look at the next point, that would be 1, 2. And then we'd have 2, 4, then 3, 8, and then 4, 16, so on and so on and so on. So with that, now we're going to look over at the logarithmic functions. So what's going to happen is exponential functions and logarithmic functions are actually inverses of each other. So with that, we're actually going to flip the pattern. So instead of doing add multiply, now we're going to do multiply add. So if I look at my table here, so now the x values we're going to multiply by 2. And then the y values we're going to add by 2. Hello. There we go. So an example graph here. So with a logarithmic equation, since it's actually an inverse, instead of having a horizontal asymptote at y equals 0, now we're going to have a vertical asymptote at x equals 0. So now my asymptote here would be at x equals 0. And then your graph is going to look something like, nope, something like that. So with your equations here, so we're going to have, whoops, 1, 0, and then the same equation, or the same points as up here, so then 2, 1, and then 4, 3, and then the next one would be, 8, 5, yes. So meanwhile, it's going to follow this pattern, essentially. So now looking down here, we're looking at these tables, we're going to determine whether it's going to follow an exponential or logarithmic pattern, or if it's not going to be either one. So if I look at this first table, so table A, my change in my x values are going to be plus 1, whereas my change in my y values are going to be times 1/2. So I have an add multiply pattern, so add multiply, which tells me this is going to be exponential. And if I look at table B over here, I'm going from 10 to 30 to 90 to 270 to 810. So that's going to be times 3. And then the change in y's is going to be plus 10. So I have a multiply add pattern. So multiply add, which tells me this is going to be logarithmic. Okay, and then same idea for C and D. So now we're going to get into the key characteristics of the actual graphs themselves. So kind of like what we already talked about, we're looking at the general form where your b value is going to represent your base, and then your a and b values are constants where a can't be equal to 0 and b cannot be equal to 1. So this is your general shape of these logarithmic graphs. So based on your transformations, we may also do reflections. So if your a value is negative, it's going to change the direction in which your logarithmic function is going to go. So same idea as exponential with these logarithmic functions. So it's either always increasing or decreasing, and they never switch. And then it's either always concave up or concave down, and then they will never switch. So with your end behavior, now what's going to change is because of your vertical asymptote, you're going to have to determine what the vertical asymptote is, and then if we're going to be approaching that vertical asymptote from the left or from the right. So we're going to get into that as we get to the specific problems. So looking here, so I have the graph of f of x. So looking at this graph, I have a vertical asymptote, which I'm going to say is going to be at x equals 0. And then notice how my graph is on the right side of that asymptote. So my limit notation for my end behavior as I go to the left, we're not getting closer to negative infinity. We're getting closer and closer to the vertical asymptote, which in this case is going to be 0. So what you're going to do for this one is you're going to say the limit as x is approaching the vertical asymptote, which is 0, and then we're on the right side. So we want a plus sign as an exponent. And then of f of x, and then you're going to include the direction in this next part. So since we're going down, that's going to be negative infinity. And then my right behavior, so as I go right, it's going to go up indefinitely. So my limit as x is approaching positive infinity of f of x, that's going to equal positive infinity. Okay, so now with the next one, so same idea, we're going to have a we're going to have a vertical asymptote at x equals 0. So my left behavior, as I go to the left of my function, we're getting closer and closer to my vertical asymptote, and we're on the right side, which means I need a plus sign in my limit notation. So my limit, and then we are graph of h of x. So make sure we use the right letter. So my limit as x is approaching 0 from the right side of h of x, we're going up, which means I'm going towards positive infinity. And then for the right side, I'm going to be going down indefinitely. So that means the limit as h approaches positive infinity of h of x is going to be negative infinity. So now for number 16 here, we don't give you a graph, we give you the equation. So with this one, so I need to factor out that b value. So I'm going to have 2 times log base 3 of negative parentheses x minus 4. So I'm going to have a reflection over the y-axis, and I'm going to go right 4. So what this tells me is my graph is we're going to have a horizontal asymptote at x equals 4. And then because of the reflection over the y-axis, instead of going up and to the right, we're actually going to go up and to the left. But we're going to be on the left side of the asymptote this time. So my graph is actually going to look something like this. So with this graph, oh my gosh, this cable, go away. So looking at the left behavior, as I go to the left, as I approach negative infinity, I'm going up indefinitely. So I am g of x in this case. So my limit as x is approaching negative infinity of g of x is going to be approaching positive infinity. It's going up indefinitely. Now, when I look at the right behavior, I'm going ideally all the way to the right as much as I possibly can, but that's going to be approaching the vertical asymptote of 4. And then we're on the left side of 4, so I want 4 with a negative sign in the exponent. So my limit notation, I'm going to have my limit as x is approaching 4 from the left of g of x, and we're going down, which means I want negative infinity. All right, moving on. Now we're going to look at increasing, decreasing, and concavity. So same idea with exponential. So my graph here is going down, but we're concave up. So it's decreasing, but concave up. So in this case, we're decreasing at an increasing rate. Then 18, my graph is going up, and we're still concave down since it's facing downwards. So in this case, we're increasing at a decreasing rate. And then with number 19 here, so I like to draw the graphs. I'm a very visual person. So we have a reflection over the x-axis. Nope, we don't. Over the y-axis. So originally my graph would look something like this, going up and to the right, but because of that reflection, we're going to go up and to the left. Now, we don't have any horizontal shift, which tells me my vertical asymptote, in this case, is going to be at x equals 0. Which, in this case, doesn't really matter, but just to kind of give you that practice with what is expected, especially for limit notation. So in this case, my graph is decreasing and we're concave down. So this is going to be decreasing at a decreasing rate. And then over here, we're going to be solving for missing values in your tables. So we're still going to be referencing like the multiply add or the add multiply. We're looking at just whatever the missing values are. So in this case, so if I look at my functions, my function tables rather, so I'm going from 1 to 2, and then 2 to k, and then k to 8, and then 8 to 16. So I know if I look at my known values, 1 to 2 and 8 to 16, I want those changes to be by the same rate. So that means I would have to multiply by 2 on both of these. So if I multiply by 2, that means my k value here would be 4, and if I multiply by 2 again, that does give me 8. So what that tells me is that my k value here is going to be 4. Which is down below, but you know, the same idea. Now looking at the next one. So if I look here, so this is going to be multiplied by 3. So times 3, times 3, times 3. So if I want to go the other way, I'm going to divide by 3. Which means 6 divided by 3 is going to give me a k value of 2. So I have a k value of 2. Okay, and then over here, let's see. 4 times 5/4, but that wouldn't work. So let's try this. So if I do plus 1, plus 2, interesting. Okay, so this is going to kind of go into, what's it called? Kind of like a second difference idea. So what this tells me is when it's exponential or logarithmic, your change should be multiplicative. So meaning my change of my change here, it should be, let's not use pink, it should be times 2. So if I have another change here that's times 2, what that tells me is that this should be plus 4. And then if I do that change times 2, then that means the next change should be plus 8. And we're going to see if we get the same pattern. So let's see if it's consistent. So 4 to 5 to 7, and then 7 plus 4, which would give me 11. And then 11 plus 8, which gives me 19. So it works. So then this tells me I'm going to have a k value of 11. So the key here is when I'm looking at the change of a change, for exponential logarithmic, it's going to be a multiplicative difference, not an additive difference, which would be like a quadratic, like a second difference. This would just be multiplicative. So over here, now we're going to get into some exponents. So with this one, if I look at my change, so I'm going from e to a negative second power to e to the first power. So I would have to add an exponent of 3, which means I would multiply by e raised to the third power, which that's the same as this over here, times e raised to the third power. So if I do my same change over here, so times e raised to the third power, I would do e to the first times e to the third power, which means you would add those exponents, which means this would be e to the fourth. That's a 4. Ta-da. Okay, now we want to find the domain and range of the following logarithmic functions. This is really going to be important for your horizontal transformations. So if I don't have any horizontal transformations, then what that tells me is your function is just going to go up and to the right, and we're going to have a vertical asymptote at an x value of 0. So with this, what that tells me for the domain is we would go from 0 to infinity, but then the range, we're going to be all real numbers because it goes up and down indefinitely. So if I look at 25, so we have a reflection over the x-axis and a shift right 3. So a reflection over the x-axis, instead of going up and to the right, now we're going to go down and to the right. So I still have a vertical asymptote, and that's going to be where the horizontal shift is, which means we're going to have vertical asymptote at x equals 3. So my domain in this case, so we're going to be going from a value of 3 to infinity, and then the range would be from negative infinity to positive infinity. Okay, and then 26. So we need to find what the horizontal asymptote is. So I'm going to set the middle equal to 0. So I would do 2x plus 3 equal to 0. So when you solve, we're going to get an x value of negative 3/2. So that tells me this would be my vertical asymptote. So when I draw, I don't have any, what's it called? I don't have any reflections anywhere. So my graph is still going to be up and to the right. But my asymptote, my vertical asymptote, is going to be at x equals negative 3/2. So what that tells me in terms of domain, so we're going from negative 3/2 to infinity, and then from negative infinity to positive infinity. All right, and then these are going to be similar problems when we did exponential functions. So we're going to be looking at transformations, the asymptotes, increasing, decreasing, concavity, graph is, et cetera, et cetera, et cetera. So with this one, luckily enough with logarithmic functions, we're not going to worry about rewriting them. We're just going to look at them as is. So with this one, your parent function per se is going to be the log base. So the parent function would be log base 4 of x. So the only transformation I have in this case is going to be that 5. So that tells me I'm going to have a vertical dilation of 5. So my graph, I don't have any horizontal transformations, so it's still going to go up and then to the right. And then my vertical asymptote is still going to be at 0. We're going to pretend that that's close enough to 0. So in terms of my asymptote, we are at x equals 0. And in this case, if I look at my graph shape, we are going to be increasing, but we are also concave down. So what this tells me is that I'm increasing at a decreasing rate. And then in terms of domain, I want everything to the right of that asymptote. So that tells me I want from 0 to infinity. And then for the range, I'm going to go up and down indefinitely. So that would be all real numbers. And then for your end behavior, I would say this is probably going to be the tricky part for most people because of the asymptotes. So check the letter. I am using f of x. So I'm on the right of the asymptote. So what that tells me, so I want the limit as x approaches the vertical asymptote of 0, and I'm on the right side of the graph, or right side of the asymptote, rather, of f of x, and that's going to equal negative infinity. And then my limit as x is approaching positive infinity of f of x, that's going to equal positive infinity. All right, and then let's do, we'll do 28. I'm looking for specific ones to do. Okay, so with number 28, so I'm going to look at the parent function first. So in this case, the parent function would be log base 2 of x. So my transformations, I have the negative out in the front, which tells me a reflection over the x-axis. And then I'm also going to go up 4. So in terms of my asymptote, I don't have any horizontal shifts or anything like that. So my asymptote is still going to stay as x equals 0. Now we do have a reflection over the x-axis. So instead of going up and to the right, now I'm going to go down and to the right. So this would be your general graph shape. So that tells me I'm going to be decreasing in concave up, which that tells me I'm going to be decreasing at an increasing rate. Okay, and then my domain, I want everything to the right. Should have drew my asymptote. I want everything to the right of my asymptote, which means my domain is going to be from 0 to infinity, with my range being from negative infinity to positive infinity. And then with my end behavior, so as I go to the left, I'm approaching the vertical asymptote. So I am using, I think, G. Nope, I'm still using F. So my limit as x is approaching 0 from the right side of f of x, we're going up, so that means positive infinity. And then my limit as x is approaching positive infinity of f of x, we're going down in this case, so negative infinity. Okay, now let's do 30. I'm going to look for one that had a reflection over the y-axis. So with this one, so my parent function that we're going to focus on is going to be natural log of x. But when I rewrite, so I do need to factor out that b value. So when I rewrite, we're going to have natural log of negative parentheses x minus 5. So my transformations, I'm going to have a reflection over the y-axis, but I'm also going to go right 5. So because I'm going right, that tells me my vertical asymptote is going to be switching up. So my typical function is going to look up and to the right. A reflection over the y-axis now means I'm going to go up to the left. And then my vertical asymptote, we are looking at an x value of 5. So for my asymptote, we have an x value of 5. And we are decreasing in concave down, which means we are going to be decreasing at a decreasing rate. That is terrible. Then the domain, so we want everything to the left of that vertical asymptote. So I want from negative infinity, that's terrible, to positive 5, with the range being from negative infinity to positive infinity. So my end behavior, so my limit as x is approaching negative infinity, am I still using f? Yes, I am, of f of x is going to be equal to positive infinity since we're going up and to the left. And then for my right behavior, I'm going towards that asymptote. So I want my limit as x is approaching 5, but from the left side, since we're on the left of the asymptote. And that's going down towards negative infinity. All right. Now, the rest of these are really just kind of renditions, and I even threw in some exponentials. Really, all I can tell you is just rewrite. Draw little mock pictures of your graphs, and that will definitely tell you about your end behavior, the increasing, decreasing, concavity, the increasing at a decreasing rate, whatever. So I just really encourage everyone to just do a visual, just like I did over here. So make good choices.